Hi everyone. This video is going to be covering two sections, and it's the last two sections on Chapter 3. This last part is about higher order differential equations, so differential equations that are higher order than second order. We'll start off with a statement saying we know from previous sections that solving constant coefficient, second order, linear, homogeneous differential equations can be simplified by assuming y is equal to e to the lambda t. So as an example, we can look at something like this. Plus y is equal to 0. And if we assume y is equal to e to the lambda t, then that gives us lambda squared minus 2 lambda plus 1 is equal to 0, and from there we can figure out that looks like this is lambda minus 1 times lambda minus 1 is equal to 0, so lambda 1 and 2 are equal to positive 1, and that means that y1, or one solution, is going to be equal to e to the t, and a second solution for repeated root there is going to be t to the t. A similar technique can be used, or we'll say we can say the exact same thing. We can say the same for higher order differential equations. As well. So here's an example. Let's say we're looking at a third order differential equation. So that's 1, 2, 3 plus 2y double prime is equal to 0. And I'm going to give you I'm going to make this an initial value problem just to show you what that looks like as well. So let's say I have y of 0 is equal to 0, y prime of 0 is equal to 3, and y double prime of 0 is going to be equal to negative 8. Okay. So it's a third order differential equation, so we need 1, 2, 3 layers of points in order to solve for C1, C2, and C3 here. But back to this differential equation, if we assume, like we did last time, that y is equal to e to the lambda t, well, then what we'll end up with is that this third derivative of lambda is, third derivative of y is going to be equal to lambda to the third, and the second derivative of y is going to be lambda squared, and that's going to be equal to 0. And we're still just solving for lambda, so we can factor out a lambda squared here. And it turns out that we have one root here. I'll call this the third one. Lambda 3 is going to be negative 2, but lambda 1 and 2, so if we want to plug in a value for this, we can plug in 0. That would make this true. And now instead of having just a y1 and y2 to associate with our lambda 1 and lambda 2, now we have y1 could be e to the 0t, so that's just 1. y2 is going to be, so it can't be e to the 0t because that's already 1 and that's going to be repeated, so we just multiply it by t. And then y to the third is going to be associated with this one, so that's e to the negative 2t. Just in the same way, when we want to come up with a general solution for this, you can probably guess what I'm going to change about this for my third order differential equation. And that is, I'm just going to add a third constant times my third solution. So turns out that my general solution for this one is going to be C1 times 1 plus C2 times t plus C3 times e to the negative 2t. I was given some initial points for y and y prime and y double prime. So I'm going to go ahead and plug those in. Remember when we had a second order differential equation, our task was to figure out what y prime and y double prime were and plug them into the differential equation. I am going to do that here. So I'll say this is my general solution. And then from here on out, I'll be finding the unique solution. So y prime is going to be equal to, well, this term is going to go away. This term is just going to become C2 times 1. And then this last term is going to be negative 2 times C3 e to the negative 2t. Y double prime is going to be equal to, let's see, this term goes away. And so what I'm left with is 4 times C3 e to the negative 2t. So now we're going to impose those points. So we have that y of 0 is equal to, let me remind myself,